Okay, let's look at a typical Bernoulli problem in Chapter 3. This one makes use of the Pitot phenomena that we saw last Thursday in the lecture. So this is problem 3.81 in the textbook. So we have this kind of strange shaped tube here with two diameters, one big diameter going down into a little diameter. So there's going to be a constriction here, so velocity is going to increase, as you see from homework number 1, where you have that tube that's decreasing in diameter. The air is coming in the big end, and it's hitting this pitot right here. And so that's going to be a stagnation point, right? And so basically we're using this pitot tube to change the velocity into a pressure, and that pressure will show up as this differential in the manometer here. So a little bit of manometer in here as well. So we're using some concepts from chapter 2 and putting them into chapter 3. So it's steady flow. We want to know what the Q is. So this is a Bernoulli situation, and we're going to go from 1 to 2 in Bernoulli. We're going to equate those two places. So at one side we have at point 1 over here, we have pressure 1 divided by gamma air plus v squared 1 over 2g plus z1 is equal to p2 squared over gamma air divided plus v2 squared over 2g plus z2. Now you notice I've already crossed out z1 and z2 because they're at the same elevation, so there is no point in tracking the z. And I've crossed out v2 because v2 is at a stagnation point, so that's a key issue right there. Remember, right here is the stagnation point, so that allows us to assign that velocity 0. So that helps a lot. So we basically have two pressures and one velocity here. So we can rearrange this. But first let's look at the manometer. So we have to remember how to do the manometer equation. Let's again go from point 1 to point 2. But now we're going to go through the manometer approach, right? So if we start at 1 and we go down h, so we get gamma air plus h. That's going to be small, right? But let's just go through the motions here. Then we're going to cross over to this side, and we can go all the way up to 2 because we're in one fluid here. So we're going to first we got to go down through the air. Excuse me, I forgot about that part. So first we go through the water. So we go through the water. So we add H1 in terms of gamma water, and that's going to be equal to the pressure at 2 plus the gamma air, the height there. We're going to lose that gamma as we go up. So again, that's going to be small. So the gamma air is whenever we have a water next to it, we can just skip the air part. So we get rid of the air, get rid of the air. We have a pretty simple manometer expression. It says the pressure at 1 and 2 is just given by the difference in height in the manometer times gamma water, which is how this manometer is designed, right? So now we can put number 2 into number 1 here, because we had two unknowns here. We have the P1 and the P2. Now we know P1 as P2 as a function of P1 or vice versa, so we can plug in. And our revised Bernoulli equation looks something like this. And we can simplify and get this kind of square root term for V1. Start plugging in numbers at this point, and you find a velocity is about 40 meters per second. And then we use continuity, remember. There's a good chance to exercise our continuity memory. And we know that we want the flow, right? That's what the problem asks for. We take that velocity and we take it times the area of cross-section 1, which is pi r squared for the big tube, and we end up with a flow of 1.26 meters cubed per second. So let's walk through that one more time. First, we set up Bernoulli. going from 1 to 2. Then we use the manometer because our Bernoulli equation leaves us with one equation and two unknowns. We don't know the pressure at those two places, but we can find out the pressure in terms of the manometer. Then it's just a matter of substituting in for one pressure or the other. In this case, we substituted in for pressure 2, and we ended up with only one unknown now, which is the one we want, essentially, the velocity. The velocity becomes this square root term. And then we have to remember that once we have the velocity, they're actually asking for the flow. So we simply take the velocity times the correct area, and we'll get the flow rate.